Hello there. Today I'm going to talk about gradients. What actually are gradients? Okay? Well, gradients are important to Obi-Wan Kenobi, of course, because he had the high ground. But that's another story. It's effectively a measure of steepness, how steep something actually is. It doesn't have to be straight lines, it could be curves, okay, but it's just a measure of steepness. And steepness is very important to our everyday life, whether you're about to come up to a hill, both uphill and downhill, or whether you're considering what is the steepness of a straight line graph that's been given to you. I'm just going to talk a bit about what we mean by steepness and gradients. So first of all, the real life application. You've come across this sign probably and thought, something's about to happen, the road's about to get steeper, okay? But what actually does that 10% actually mean? Well, I'll tell you, 10% as a fraction is 1/10 or 0.1. What that means is for every metre you're travelling horizontally, you're gaining height of 1/10 of that. You're gaining 1/10 of a metre in height. Visually, it looks like this. So here's a metre ruler, and here's a highlighter pen, which is 1/10 of a metre, so 10 centimetres. So for every metre you're moving horizontally, you're gaining height of 1/10 of a metre. Okay? It doesn't matter what the units are, whether it's kilometres, miles, inches, it's always the same. 1 unit of travel horizontally gives you 1/10 of that vertically upwards. And that's what the 10% means. So it's quite an international sign, that, because whether you're in Europe doing kilometres or whether in UK, America doing miles, the 10% means the same sort of steepness. So you might think it's not very steep, but you'll notice it if you're walking or if you're cycling. This is what it looks like here. The diagram's not been drawn accurately. This is an accurate representation. So here you have 1 unit travelled, so I've deliberately not put in the units, you see, means you've got 1/10 of a unit gained in height. And I've just created a right angle triangle there because that's the actual path, but this is mathematically, physically, if you like, what's actually going on. That's what's happening when you're coming to that. Of course, it looks a lot steeper, doesn't it, than it actually is. Okay, but that's always the thing about real life. It generally feels a lot steeper than it actually might seem to be. What about this one here, the 20% downhill? Now, even if you don't know what the 10%, 20% actually mean, you can figure out if you're driving, you need to start thinking about your braking, your gearing, because you're about to start going downhill. It can be quite dangerous if it catches you unawares. So this time what's happening is that unit of distance you're travelling horizontally, you're actually losing twice as much as we gained previously. What does that actually mean? Well, the 20% as a fraction is 2/10. Okay, 2/10 of a metre, 20 centimetres. It means you're actually going downhill this much. Okay, so for every metre you're travelling horizontally, you're travelling downwards effectively 2/10 of that, and that's what it looks like from a visual point of view. Diagrammatically, again, not down to scale, looks something like this. Okay, so for every metre you're moving horizontally, you're effectively losing 2/10 of that. And again, the units, they do not matter. We call this a gradient, a positive gradient, because it's uphill, and a negative gradient simply because it's downhill. So what would it be if you're just moving along a flat line? Don't say straight line, because they're all straight, aren't they? Flat line, horizontal line. You guessed it, gradient of 0. And here are my fun diagrams to show you that. So someone is going uphill. I don't think I'd like to be that cyclist. It's a bit too rocky for me. Downhill, again, I don't think I'd like to be that person going down. Again, that's a bit too bumpy. Yeah, that's more my thing, but obviously I'm a bit less glamorous than that. So travelling flat horizontal, it's a gradient of 0. Okay, so you get the idea. So gradient of 0, essentially because it's got no steepness at all. Whereas if you're actually moving uphill, you've got a positive gradient. If you're moving downhill, you've got a negative gradient. Okay, get all that? Great. That's what gradients are. Okay, just get rid of this. Could do one of those, but one that lights up. You should invent one of those. I raise the hand. It's called a lightsaber. In terms of the maths that you'll learn at school, this is pretty much what it's about, graphs. Okay, because pretty much everything can be drawn as a graph when we're dealing with gradients. Okay? We would like to know how steep that line is. Okay? Why is that? Well, because we'd like to be able to compare it with other lines. You can visually see which lines are steepest, okay? But mathematically, which line is the steepest? How can we calculate it? That's why we need a numerical value of the steepness, okay? So we can give, rather than just say, oh yes, this green line here looks steeper than the red line, therefore is steep. We need a mathematical calculation. What about the green line, the blue line, for example? Are they the same gradients? Okay, is there a slight difference? You need to calculate it, and that's why we need to learn more about this. That's why gradients, in this context, will be quite useful. Getting back to this one. So remember what I said about the road signs. So I was saying something along the lines of you're travelling horizontally and you're gaining height. Okay. So what I'm going to do is I'm going to pick 2 points. Not that one because it looks a bit unclear. I'm going to choose that point there. I'm going to write down the coordinates for you. That's got the coordinate 2, 1. There we are, 2, 1. And I'm going to choose another point. Just choose that one there. Relatively far away, so visually it looks nice on my video. That's got coordinate 5, 7. Okay. What we're going to do is we're going to look to see how far horizontally we're moving from this point to this point, and how far vertically. I'm going over this clearly so you can see. And notice I've drawn a right angle triangle there. Let me just recreate that for you. Here is the right angle triangle. And we're just going to work out how far we're moving horizontally and vertically. Now, we're not moving 1 metre or 1 unit horizontally, are we? We're moving several. So I'm just going to count them, okay? So 2 to 5, that's 1, 2, 3. Can you see? Effectively, horizontally, the distance is 3. And vertically, can we count the vertical distance? So 1, 2, 3, 4, 5, 6. Do you agree with that? So from 2, 1 to 5, 7. Just be careful about counting squares. I've done this so it's nice and easy. Sometimes 1 square does not represent 1 unit. You must check on the scaling on the graph. Okay, but for this purpose, it actually does. So basically, for every 3 we're moving across, we're moving 6 upwards. Okay. What we're going to do is we're just going to divide this by this to get our comparison of how far we're moving upwards, moving 1 unit horizontally. 6 divided by 3 is 2, so that means our steepness is 2. What that means is for each unit move horizontally and move vertically upwards 2. Okay? And that's what we call a gradient. Right? We call that gradient 2. You can see it's a positive gradient because it's sloping upwards. And what that means is, let me just erase some of this. For every unit, let's just say we start here, for every unit we move horizontally across, we move 2 units upwards. That's what the gradient means. I'll do it again. For every unit horizontally, 2 units upwards. For every unit horizontally, 2 units upwards. Always left to right, of course. That's the natural order of things in mathematics, if you notice. Okay. So back to these then. You will be able to work out the gradients of any of those lines if you wish. Look, if you want, just take a screenshot, do it yourself if you wish. I'm not about to go over the answers to those. This is just a video in what gradients are generally all about. Okay? Just some more examples to complete this section. When you get on to year 10, year 11, or even beyond, you'll start to consider gradients of other functions, other things that are not straight lines. How do you do this? So I've just taken this from a year 12 question, actually. The graph shows the curve of the equation y equals x squared. It's a lovely parabolic shape. Just remember that word, parabola, parabolic, for when you do quadratics. It's a lovely word, isn't it? Parabola. Check out my other video on parabolas. I went to Porto to do a whole thing. Anyway, find the equation of the tangent to the curve. So a tangent is a straight line that just touches the curve at a particular point. There, we're trying to find the steepness of that is, because the steepness of that tangent tells us the steepness of the curve at any given point. Notice that the curve is increasing in steepness as you move from left to right from this point here. It's increasing in steepness. And you'll discover that there's a whole section called calculus, wonderful section of mathematics, calculus, that will help us to do this far more easily than drawing tangents. Anyway, that's just another application of gradients. Let me show you a couple more. Travel graphs, you've probably seen these already. Travel graph, so distance travelled in time, seconds. What would happen if we work out the gradient between 2 points? I'm going to choose 2 simple points, like here, 0, 0, and here, 10, 70. What I'm thinking about is how do we work out the gradient between those two? How steep is that graph between here and here? Maybe you can do it already. Maybe somebody got the answer already. Hold on to that thought. So how far are you moving horizontally? 10 units. Forget about the units for the moment. Seconds, I know. and then vertically it's 70. Now, I'm not saying about the scaling, sometimes it's not always 1 square is 1 unit, so you've got to look at the actual scale that's being involved. And 70 divided by 10, we always do the vertical over the horizontal. Okay, 70 divided by 10 is 7. Yes, so the gradient of that straight line is going to be 7. Who can interpret that for me? What's the interpretation? Give you a few seconds to think about it. Consider the units. We're travelling in metres over a time of seconds. That gradient is 7 metres per second. That's why it's important that you get the idea that the gradient is about how you're moving horizontally and then vertically. Okay, for every unit you move horizontally, you move vertically. Essentially what that means is for every 1 second you're moving 7 metres. Okay? 7 metres per second. That's a speed, isn't it? It's a speed. So the gradient on this distance time graph allows us to work out the speed. Isn't that amazing? Isn't that absolutely fantastic? Because knowing how fast someone's travelling is rather important. And you can extend this further. You can work out accelerations as well. And we do a lot of that in year 12, year 13 when we do mechanics. And you probably see a fair bit in physics as well. Now I've got one more example of gradient to show you. You might recognise this, maybe. Okay. Check it out. This is episode 2 of The Big Bang Theory. Fantastic show. Absolutely amazing. I do love it. What's the relevance for this? Well, they consider how they move this. Some people just move it. But these, of course, being the brilliant physicists, they are doing just natural calculations. They've got what's called an inclined plane, a slope. And a lot of the time, we're modelling a slope, an inclined plane like this. Here's an object on an inclined plane. Sometimes we're given this angle. But clearly we're interested in, you guessed it, the steepness of that inclined plane. So it all goes back to this thing about gradients, doesn't it? Okay. I'm hoping you got a lot out of that. I'm hoping it gives you some sort of idea as to why gradients are important to us, not just in mathematics, but in the real world as well. Thanks for tuning in, and I'll see you again.